All right, guys. So I'm going to take you to, well, actually, it's taking back to mechanics one more time. Yeah.
Okay.
So what we are doing right here is now I'm going to bring back the Newton's law, the beloved Newton's law, sigma F equal to ma. But there is another aspect of this one that will lead you to another kind of motion. You probably have done like a straight line motion. You did two-dimensional motion like projectile motion, circular motion, or you even extend your description to three-dimensional using vectors. You have like a displacement vector, velocity vectors, acceleration vectors. They're all in 3D using vectors notation. Everything works. But there is another kind of motion that you have to understand, because it has a very, very useful applications later. And that motion that I'm talking about is oscillations, guys. So when you say oscillation is something that is going back and forth, back and forth. So that means you are talking about something that is having an oscillatory behavior. So things just go back and forth, back and forth, back and forth repetitively. That's the oscillations. All right. And the application that links directly to this oscillation is waves. So this is a huge, huge portion of physics material that you have to understand and study, because, well, wave is like, it's going a really, really long way, all the way to quantum physics. You still use the concepts of waves to explain quantum phenomena there. So that's why I think understand oscillations will give you a very, very good background in understanding waves. Once you understand waves, that is a very good background for you to understand other things in nature, in the future and everything. Yeah. And it also have technological implication as well, because you communicate things through waves all the time. Yeah. Radio waves, light wave, sound waves, and everything. So it's very important here. Okay. So this is like the first episode of this whole thing. We're going to learn about that motion we called simple harmonic motion. Okay. All right. And
Okay.
for the rest of the stuff, we are going to do that later in the next lecture. But today, let's focus on this. What does it mean by simple harmonic motion? Yeah. All right, guys. You wouldn't believe that today's lecture is going to be super, super simple. Wow. Seriously. Right? When I say simple means you start from something so simple, which is Newton's second law, sigma F equal to ma. But the result that you're going to get out of this is super automatic. It's like you don't have to implement anything at all, given that you know mathematics behind everything that we're going to learn today. So today is going to be math heavy lecture, because what we are doing over here is it's going to be some calculus with its differential equation. So here we go. All right. So first of all, guys, the system that we are looking at is this. When I said simple, yeah, don't be afraid, right? Yeah, don't give me that emoji just yet. You will see at the end, we are not learning mathematics. We're learning physics. So I'll just take away that complications at the end. So there'll be some take home messages for you. Yeah, for those of you that don't really want to pick into detail or anything. All right. But anyway, when I said simple, it's seriously simple, guys. Look at this. Look at my system here. That's mass. That's one mass here. And there's a spring. So it's a simple mass on spring system. Okay. So if you want to analyze the behavior of this system by using Newton's law, what will you do? Well, no problem. Let me start by writing down the force diagram. We're just doing like a free body diagram and whatever things that you did before. You just, hey, what are the forces that acting on this mass? And once you know all the forces, then you just do sigma F equal to ma, and you're pretty much done. Sounds cool?
Okay.
So let's do that. Guys, how many forces acting on this mass? First of all, let's assume that the floor has no friction. Whoa, that's even easier. All right. So when no friction, the only force that acting on this mass at this particular spot is just the spring. The spring itself is trying to pull the mass to your left. So let me write it down one more time. Is F with the subscript S. That is for the spring force. And it's pointing to your left. It's the same thing. The one on this one. They are the same thing. I'll just rewrite it on overlay on top of the mass here. That's all. So that's it. Done, guys. This is it. Today's lecture is this. Whoa, seriously. And how can you explain this force over here? You guys still remember Hooke's law that you use in spring? Hooke say the spring force is proportional to the positions, which is you can talk about in terms of displacement of that spring, which means in this point it's the position of the mass. So if X is being stretched, so it means X is positive, you will get some sort of like a positive force. Oh, well, let's talk about the sign a little bit later. But anyway, it depends on the magnitude of X. The bigger the X, so it means the larger the stretch or compression, it doesn't matter because we talk about the magnitude right now, the greater the force, the spring force, right? So that's fine. However, because force is a vector quantity, so that means you need to put the sign in front of it. And if you look at this one, X is also a vector quantity because it's a position. When it's a position, then you can say, okay, the position of this mass is right here. So I put this as an X vector. So as you can see right now, the vector X pointing to your right, but the spring force is pointing to your left. So that is a significant, I mean, this is sort of like signifying that the force will pointing in the opposite direction to the direction of the X vector. Is that good? So this is the reason why if you would like to express this Hooke's law in the vector form, you need that negative sign in the front all the time. Okay, take a look one more time down here. All right, when the mass is right at the equilibrium point of the spring has no stretch or no compression, no spring force, so no problem. The force of the spring is 0. Cool. Come down here. Now, when the spring is being compressed, at that point, your X is pointing to your left. That's your X vector. But then, of course, at this point, spring is pushing the mass outward. So your spring force point to your right. And that's perfect. So the expression we got on top works for the spring force. That is done for this Hooke's law. So that's Hooke's law. Cool. All right. So that is it. You have only one mass, you have only one spring, you know the force from the spring that acting on that mass. We apply Newton's second law right away. Sigma F equal to ma, guys. Sigma F equal to ma. See, I'm writing everything in terms of vectors, of course. However, because what we're doing over here is just one dimension. Everything is just doing movements and everything is only on the x-axis. And we still sort of like, yeah, okay, it's a one dimension problem. So let's take a look at just the x component of this. So all I need is just extracting the x component out of that one. And because sigma f in the x direction is just the negative kx. With me, guys? And because we're already on the x-axis, so that's why sometimes you don't need to put that arrow sign on top anymore. Forget about it. Okay. However, you have to make sure that this is still a vector equation. So it means x still have a positive and negative value. Positive means it's to the right of your origin. Negative x means it's to the left of your origin because it's representing the displacement vector. Cool? Got that one. Okay. So with that, sigma f equal to ma. Sigma f, you only have one term, negative kx. That's nothing else. And you equate that to m times a along the x-axis. So that's why a sub x. This is it, guys. We call this equation of motion. What does it mean? It means this equation will tell you everything about this motion of the mass. That's why I say, hey, guys, this lecture is done right here. That's it. I don't have anything else. It's so simple. Sigma f equal to ma, I'm done. However, the detail that's follow is this. The a turns out, all right, everyone knows, you can rearrange these terms a little bit, and I just put everything else to the other side of the equation. So that means you can find out the acceleration of this mass. It's going to always be equal to negative k over mx. Check. No big deal. But you still don't know what the x is going to be because you really want to solve for x. You want to know where are those positions, blah, blah, blah. So you know that acceleration is the second order derivative of x with respect to time. So this means I can rearrange or rewrite that as a relation as d2x by dt2, guys. And that's it. Let's zoom it in. Huge. This is differential equation that I'm talking about. Woohoo! Right here. Okay. This is it. And we want to solve for x. My question is, do you know how to solve this one yet? Can you? Or have you done this before? That's the question. So you're asking yourself, Ajahn, what is going to be the x that once it gets differentiated twice, you get the original back with some factor in the front and along with the negative sign. Okay. If you know this x, that's it. That is your solution. Cool? This is very short. And this is what second laws give you. Sigma f equal to ma give you this. So your task that you have left to do is solving this equation. If you can find your final answer, of course, final answer will be some x as a function of time, because time is your variable. X is the function that you want. So at the end, you're going to get x as a function of time. So if you have x as a function of time that fits into this equation, that is your solution. All right, so I'm going to show you how to solve this one. And I hope the good thing about this one is once you know how to solve this, it turns out you will be able to solve this kind of equation for the rest of your life. Seriously, just like you know how to ride a bicycle, just something like that. All right, so once you know it, you know it. And once you see it again in the future, bam, you know it. There's nothing else for you to know. All right, so we're going to take this thing down once and for all. And then in your life, you don't have to worry about this kind of equation anymore. So I'm going to start very simple, guys, with this. Answer me this. Hey, I have d2x by dt2, but just to make things a little bit simpler, I just equate that to negative x. So forget about that whatever coefficients in front of x at this point. Just answer me this. Hey, guys, give me the x. That is the solution of this equation. You have any suggestion at all? Woo. All right, maybe it's just annoying. Anything? Any kind of x that have this property? And I think I'm going to review a little bit of like the math back in the day that you study since like you were like in middle schools or high school. There was some reason why. If I ask you this, guys, how many class like family of functions that you have learned in your life? Seriously, in your life. What do you think? Right? How can you classify the functions, mathematical functions that you have learned in the past? You probably think of it, okay, I can imagine like there is like a power function, like polynomial and other stuff. So it means you talk about the family of like x squared, x cubed, or I can sort of solve like put square root of x, like a cube root of x, or you can put like an, I don't know, whatever, something that has some numbers on it. That's one class. Cool. The second class that you're probably thinking about is probably, Ajahn, you can do exponential. So you can do like constant to the x or e to the x. Yeah, the more common one. Another class will be probably the inverse of this. You spend a lot of time doing that. So you have log of x, maybe natural log of x, stuff like that. And then the last class that I can talk about is trigonometry function, sine, cosine. Okay, I'm writing x right now because most of the time you study as like x as your random, not random, as your variables, right? So these are 4 classes that you have already sort of like been studying since, you know, I don't know, middle schools and everything. I think I can give you the reason why we only focus on the main 4. And you sort of like, you know, you might have like a combination of this, or you might have like an absolute function or some weird function that you might throw into the mix. But I would say the main families of mathematical functions that you have been studying can be pretty much like, I can say that these are the big four. All right. And there's a reason behind this, guys. Look at this. If I talk about calculus, doesn't mean I'm talking about the differentiation, right? Differential calculus over here. What happened to the first family, guys? When I differentiate this, I have x. Once I get differentiate x, okay, let me write it on the side here because I don't want to mix it with what we're doing over here. So we have differentiate x, I get 1. If I can differentiate 1 again, I get 0. You guys with me? So there's no way that you can get back to itself. No. So the power function family won't give you this property. One more time. Try this. Okay, the easiest one is the e to the x. When you differentiate e to the x by x, you get e to the x. You differentiate it one more time. You also get e to the x. Well, at least you get the original back, but you don't get the negative sign. No, so no, that exponential won't do it. It doesn't have this property. Cool. Log of x. All right. If you do d log of x, oh, the internet problem maybe. Oh, internet is unstable. Okay. It's unstable. Okay. Is it back? You guys still with me? Yeah. Okay. So log of x. Yeah. Differentiate log of x, you get 1 over x. And now everything is bad because now you already x to the negative 1. Now you get back to this category of function over there. So no, it doesn't have this property. Make sense? Now back to this one. Well, hey, John, derivative of sine of x. You get the cosine x. But then if you differentiate the cosine of x again, you get negative sine x. Wow.
Okay.
So this seems to check. The trigonometric function seems to work. And actually don't have to worry about the tangents that much because tangent is just a combination between sine and cosine. So that means the big two that you're probably going to think and have this kind of property is either sine or cosine, because cosine work equally well. D cosine by dx is negative sine x. Derivative of negative sine x, you still get the negative there, and then you have the cosine x. So, okay, you start from the cosine, you get back to the cosine with the negative sign. So that's it. The way that you can have the family of functions that fit this differential equation is the trigonometric function. And to be precise, sine or cosine. That work.
Okay.
And you see how amazing this one is? See, you started from sigma f equal to ma. From that sigma f equal to ma, you are getting the, I think the internet is slow. It's not updating. Weird. You guys seeing the screen properly here? All right, guys, I'm back. Sorry, my internet was just, it just kicked me out. Nothing is running at this point. Okay, I'm back. I just switched from one to the other. So, all right, good thing that I have two network at this point. All right, guys. Okay, so where were we? All right. So I hope this one is good. All right, so that means this is a good thing that we have the trigonometric function ready for us that satisfy this differential equation. But don't forget that this differential equation came directly from sigma f equal to ma. This differential equation right here is from sigma f equal to ma. So that means it's already dictate how this mass is going to move. It's going to move back and forth, back and forth, back and forth, because that is a sine and cosine characteristics. Isn't that cool? Wow. I don't know. You feel like what I'm feeling, but it seems like mathematics is already waiting for you. And it's so nice that by just having a simple system like this, you apply Newton's second law, and then you get to the differential equation that you already knew that the solution will have the sine and cosine in characters. That's done. All right, and now let's dive into detail, shall we? Okay, so Ajahnบอก, okay, I know it. The solution should be sine or cosine. So what kind of form of sine cosine should be? So I suggest let's try this. X equal to sine t. Don't forget we need a function of t in this case. So x prime is cosine t. X double prime, which is the second derivative, is negative sine t. So check. Nice. Very good. X equal to cosine t. X prime is negative sine t. X double prime is negative cosine t. Check. That's good. So sine and cosine are both solutions to this. But wait, Ajan. Hey, Dan. You missed that extra coefficient right here. There isn't k over m that you have to bake into this one. So think about it. Well, we already have that kind of techniques. Once, back in the day that we studied differentiation. To have some numbers pop out in the front, it doesn't really be that bad, because think about this. All right, so now let me write another equation for you guys. So if the equation we want is d2x by dt2 equal to, let me write it like some alpha x. How can you get a number out in the front? So I'm going to assume this, guys. So follow me here. Let me say x is my sine, and then we'll just introduce some constants in front of x. What do you get? X prime is going to be cosine omega t. But then don't forget, we learned chain rule.
Okay.
Chain rule. You need to differentiate dip side. You have to differentiate that omega t function. So you get extra omega out in the front. Very nice. You do it again. Omega is still there. Cosine, you get negative sine omega t. And then you do the chain rule one more time. You differentiate. In there, you get extra omega out. So that's the way that you can actually have extra constants in the front, is by introducing the extra coefficients in front of time variable. Cool. And as you can see, if you introduce omega in front of t, you get double of that. So you can imagine that this alpha over here should have the value equal to that omega square. You guys with me now? So if that is the case, now you come back and compare that to our equation. You already have the factor k over m in the front. So that means k over m in the front over here will act just like omega square of us that we just saw. So that means I can say, hey, the omega that we really want to put it into our equations in the final solution should have the value of square root k over m. And that's it, guys. Sine omega t, where the omega is square root k over m, will be your answer to this equation.
Okay.
Isn't that cool? It's getting better. Yeah, getting better. All right. Not bad. But then, still not done yet. But then, wait a second. If sine omega t works, cosine omega t will also work. How are we going to deal with this? We have two types of equations, or two types of function that both are solutions to this differential equation. You guys sort of remember vaguely, for those of you that already took calculus 2? Does it sort of like give you anything? So there is a word of saying that, hey, linear combination. Does that ring any bell? Yes? Maybe? All right. So the linear combinations, there is a sentence or like a statement saying that the linear combination of all possible solutions of the differential equation still be the solution to that differential equation. So what I'm saying over here is, if you have sine omega t to be, okay, I already said it's qualified to be a solution. And they say, hey, cosine omega t is also qualified. What I can do is I can have these two and linearly combined into a bigger one, but this one is still be a solution to the original differential equation. Isn't that cool?
Okay.
All right. So that means when I say linear combination, means you can have some a of function 1 plus b of function 2 plus c of function 3, on and on. That's what it means by linear combination. It's only combined using either the multiplication by a constant factor or just additions among them. So I'm going to do that, okay? Because I want these two, and I know that these two qualify to be my solution. So what I can say is the grand general solution. All right, so this one will coincide with mathematics. Will be A sine omega t plus B cosine omega t. That's my linear combination from the sine and cosine. Isn't that cool?
Okay.
All right, so that's the basic that I want to talk to you about calculus, differential equation, and whatever things that, functions that you have learned in the past. How can that lead to the solution of our equation of motion? All right, but then that's not done yet. All right, this is still very inconvenient to use because, well, mathematical wise, this one looks nice and all. This will explain all the general solution to this differential equation, on and on. But we're doing physics, guys. Right? This one is kind of nice, but it's still not for our purpose right here. So let me give you this. First, it will be nice to have like this form of just an equation because it looks good. Looks good means, all right, I have sine or cosine function. Pick one. Pick sine or cosine. And by picking that one, you know what numbers or whatever the constant that you have in this equation will signify here. Whatever the numbers that come in front will give you the maximum value of the whole function. You guys with me here? The reason is because everyone know either sine or cosine will have the value between -1 to 1. No more, no less. Okay? So it runs from -1 to 1. So that means your x over here will only run from -a to +a. So that's why we can name the a our amplitude. That's the name for it, amplitude, because that is the maximum possible value of x or the displacement that you can go. Okay, so that's one more time. That's easy to do. That's fine. But then what about the omega? The omega, we will talk more about that one. But here is omega is going to be something that attached to the time. So eventually the omega will have some property attached to it. But anyway, our point right here is this is kind of nice and cool. If we have this form of the function, we can interpret them very easily. But when we have a linear combination like this, that's kind of like not so obvious. So the way that we can do is this. I don't know, you guys still remember the identity that we study in trigonometry, like sine A plus B equal to sine A sine B. Sine A cosine B. I don't know. I don't remember either. All right. Maybe if for those of you that still remember this one, just give me like the good, correct explanation of this. The form of this one. But I hope this one is still work. Like sine A plus B is sine A cosine B plus cosine A cosine B, on and on. Something like that. Same thing with the cosine. There will be like a cosine A plus B will be equal to blah, blah, blah. Yeah? All right. But anyway, the point is, this is good. By having this, okay, let me write it like this. It's cosine and sine with some numbers right here. See? So you can use this identity to wrap or combine or shrink down the additions between two functions between sine and cosine, and bam, wrap into just a single value of this. Either pick, it's your pick. You can pick sine or cosine. It doesn't really matter, right? For example, like this one, if I remember correctly, it's going to be cosine A, cosine B minus sine A, sine B, on and on. So that means you can still do constant cosine, constant sine. So it means when you have sine and cosine adding to each other, you can combine them into a single value of sine or cosine. Single function of sine and cosine. So that's what we want to do. So what I'm saying over here is, instead of writing down as a combination between sine and cosine, I can actually wrap these two into a single form. Okay, you can pick sine or cosine, doesn't matter. And at the end, all you need is just two terms inside your argument over here. And that's what this one is, guys. This is it. This is our general solution to equation of motion that we started out right here.
Okay.
This is where I want you to get to for the first half of today's lecture. It's right here. And I hope you now can see and understand what this is. Every time you look at this one, now you understand, hey, I know what the A is supposed to be and what's from. It's from linear combination. And when you have two terms adding to each other in the arguments over here, it means you can distribute it out and write it as a linear combination between sine and cosine. Cool? So that means from now on in the future, if you read some textbook and they said the solution to our equation of motion look like this, no problem. Okay?
Okay.
Same thing, because it's your choice. You can pick cosine or sine. Doesn't really matter. As long as you have two terms in here, you're going to be able to spread them out and write in terms of the linear combination between sine and cosine anyway. I don't know. I mean, maybe I go too far in terms of like trying to explain to you guys like why do we arrive to this form of the final solutions. But I think I try to make the connections with calculus that you have already learned, right? Because I don't want to add any new things to you. And I think what you have already learned from calculus should be able to, you know, being used here. And it should work. Everything that you have learned there is supposed to show up here again. All right? And just to make sure that you understand what the omega is, let me ask you this. Guys, we're doing physics. The omega is not just a number. In mathematics, you can just maybe you think of this one just a constant or whatever. But in physics, it means something. So let me ask you this. What is the unit of this? What should be the unit of omega? Okay, all right. Oh, scalar. Okay, very good. Yeah, it is a scalar quantity for sure. But what is, oh, very good. That's another one, is a s to the negative 1. So it's a 1/2. Very nice. So just keep in mind, the omega is being multiplied with the t. And the omega t is inside the cosine function. So one thing that you have to keep in mind all the time studying physics, when you have sine, cosine, exponential, logarithm, all these crazy transcendental functions, the argument here must include the term that is dimensionless. You guys with me? Oh, my handwriting is bad. Dimensionless. So what does it mean by dimensionless? You have never seen in your life sine of mg. No, never. Because that would be weird. Mg is like in Newton. And then what is the sine of Newton unit? There's no units like that. You never heard of like exponential tension, something like that? No, because you don't know how to do like exponential to the Newton, something like that. Or log of mass, log of m. No, these are impossible. Because whatever follows sine, cosine, exponential, logarithm must have no unit. And that leads you to understanding that what about the unit of the angle, the phi, the constant inside your cosine and cosine. That angle that you're usually familiar with, the theta, is dimensionless because it's the arc length divided by radius. Arc length has the units of meter. Radius has also units of meter. So meter cancel with meter. So what I'm saying over here is the radian units or the degree is actually dimensionless quantity. So you guys with me now? Okay, so just make sure that you keep in mind all the time that every time you talk about like, hey, 180 degree means equal to pi radian, they're both dimensionless. It's just a numbers that giving you the position in the angular sense. That's all. But in fundamental units, it's dimensionless. All right, so over here, your friend already gave you the solution, the correct answer. Omega must have the unit of 1/2 because time over here that you're seeing is already in the unit of second. So the omega must be in the unit of 1/2. And whenever you see the over second unit, what are you thinking? Is the frequency. So if you express everything in terms of the angular position in radian, this is the angular frequency. Isn't that cool?
Okay.
All right, so omega is still the same omega that you learned back in the day of circular motion. When things going in circle, you can calculate how frequent it's traveling. But then when you express in terms of radian, you get angular frequency. All right, so let me conclude over here. So actually the omega that you saw here is 2 pi over f. Same thing, same expression that you learned before. Okay, and f over here is still the same f that you learned before. It's a frequency. So it's still an inverse of period of motion, the time that it takes to complete one cycle. So that's it, guys. Oh, sorry, 2 pi f, not over f. There you go, 2 pi f, and it's 2 pi over period. And that's it, guys.
Okay.
See, so you have a connections from what you have already learned before, the things that, well, circular motion, you can think of it as a repetitive motion because it's come back to the original position and go another circle, you go around in circle. So that's repetitive as well. So that's why you have a close connection between the trigonometric function and the circular motion. And hence, those omega, the f, and the t will have the same interpretation. I don't know, does this work or not? I hope I'm not, well, go way too far from what I really want. But the point to take for the first half of today's lecture is this one right here, guys. This a cosine omega t plus phi is the general solution to our equation of motion that we derive from the Newton's second law, sigma f equal to ma, lead you to this, d2x by dt2 equal to negative k over mx. Bam, you know right away. Every time you see this equation, the solution look like this. There. That's my point over here, guys.
Okay.
Let's take a break here, and well, I'll have you, look at this one for a little bit more, and then we'll talk more in details about this periodic functions and all the stuff that it's going to follow after the break. Sounds good? All right, guys. So I think let's take 10 over here. I'll see each other again at 11, and let's come back at 11. All right, guys, take a break first. All right, guys. So what we have over here is now sort of like give you an idea that where does that oscillatory behavior comes in? The answer is, well, Newton's law just give it to us directly, and to be able to get to that sort of like the solution to that sigma f equal to ma, it's already in the differential equation. The solution of that differential equation is already built into this sine and cosine function here. Cool? I hope this one works for you. Now, just to understand this one just a little bit, that once we arrive to the solution, which we said is a general solution. So it means you can use this form to represent or to use it to explain any oscillation in this universe. I can say that.
Okay.
Anything that's come in the oscillatory form can be described using this a cosine omega t plus phi. And don't forget, just to emphasize one more time, you can pick sine. Doesn't really matter. Same thing. All right. And this similarity between, or the equivalence between the two, will become even clearer with the next explanation here. So what the reason that I said this is general and you have freedom to pick between sine and cosine is because the way that you write this one down is so general to describe any type of oscillation. Okay, so follow me here a little bit. So once again, I need an extra page here, and I hope this will give you the connections from the unit circle. I mean, if you still remember first time studying trigonometry, yeah, you have to deal with this unit circle. You have xy axis, You have a circle, and usually we say it is a unit, so it's mean the radius is 1. Yeah. All right. And all right, I'll just draw. Okay, this one I draw a nice one here. XY axis over here. So the unit circle used to map the position on the circle onto a graph, XY curve, or whatever that you want to do. But to make things a little bit more physics for us, imagine this. If you have a dot or a point that is rotating, think of this one. Look at the green dots over here. And let's say this green dot is doing a circular motion just like what you did back in the physics one there. So it's going counterclockwise, okay, and it just rotate with some angular frequency. I will call it omega, just the one that we used before. So you know how frequent this one will circle around per second, okay? But then the way that you use this unit circle back in the day was just like, hey, I'm just going to map the position. For example, if you're starting from the first one, so let me highlight this one as a black dot. And you said you are right here, right? So you might be able to just map the location in the height of this dot. When I say the height of this dot, what does it mean? The height is going to change over time because of this constant circulation here. Look at this line over here. You're going to have this one rotating like that, right? Constant omega, right? So this dot on the circle will just keep circulating around. So if you care about the height of this dot, so that means when it reaches at some height over here, there you go. So all you need to do is just mapping the height onto this graph right there. I mean, does it look familiar to you? Okay, so that means at the black dot, that is when, let's say, hey, Ajahn, I'm going to start counting the time right here. So that you start from x-axis, that is your time 0. So the position, the y, the height of the black dot is at 0 as well, right there. And then when you start circulating around this circle, the height will increase over time. Like the blue dot will show up right here somewhere in between. And of course, when it reached the maximum over here, then you're probably going to hit somewhere at the peak. There, here we go. It's already at the peak there. And then eventually it's going to lower itself down. And it's going to come down here, come back here again. And it's going to come down to the negative side of the height. And this one will come back down here again. So let me put here. And then it will just rotating, complete one full cycle, everything come back to the original position. So if you trace this position, what you are getting, you are going to get a sinusoidal curve. If I don't know if I can draw this one nicely, but I hope that's it. You are done.
Okay.
Oh, so this is pretty much like I just re-express everything that you have learned back in the day of like mapping the unit circle onto a sinusoidal curve in an XY axis. Cool? So what I'm saying over here is it means at the time over here, you can say that, hey, if you measure the angle, this is your angle over there. So let me write it like this. This you can call it theta. So at first, this is your 0 angle or 0 radian, or you can call unit degree, up to you. And once you reach over here, this is 90 degree or pi over 2. And that is right here, pi over 2. And now it's 180 degree is right there. That's pi. That's 180 degree. That's pi. 270 degree, that is 3 pi and a half. So 3 pi and a half is right there. And come back to the original position, you complete one complete cycle, 2 pi. Cool. So, and this is the reason why we don't want to speak of the theta in terms of the degree anymore, because you can see that you can use the theta to position the dot, the position that dot on the circle. So that's why usually we're going to name this phase. The theta is phase.
Okay.
But it's angle anyway. So, well, you can talk about theta to be the angle. It doesn't matter. But we just have a cool word for it. It's called phase, because we can use that to specify the angular position of whatever things that you are talking about. All right. But equivalent to angle anyway. All right. But we're going to use, usually we reserve angle for geometry, and we use phase for our waves or oscillatory behavior and all the stuff in physics here. Okay. All right. So I hope this one works very nicely, that you can pinpoint the angular position on a sinusoidal curve. 0 is here, pi over 2 is there, pi is here, 3 pi and a half, 2 pi. Now, at time 0, I don't want to start at your point. Why do you have to start on an x-axis? I want to start my time 0 over here. Let's say the time 0 is already at the top. Well, no problem. So that means for your case, you're going to start at this position over here. That's your time 0. So your curve will start at that point. And then you're going downward. And then you go down here. So it's fine. And then you go down to the negative side, touch the bottom, creep it back up to 0. And then you go back to the original position, complete one cycle again. That is fine. But you can see now the red is the sine function. Yeah, so you can say this is psi t, let's say, for now. And then the blue, that's the cosine t. So now I hope you see when I say sine and cosine are exactly the same thing, is because you just pick the different initial position. If you want to start from theta equal to 0, you get a sinusoidal wave. If you start from theta equal to pi over 2, you get cosine function. And of course, you can start everywhere else you want. For example, that I want to start from the green dots over here on the left. That means I'm going to start at pi. And I'm going to start by going downward right away. So it means that's fine. You can start from here. And you're going down first. And then you come back up. Go to the top. And then complete one cycle here. That's fine. Or you're going to start from the bottom if you want. Okay, that's fine. You want to start from the bottom. And then start to go up. Up to you. So the only thing that's going to go differently is just when you want to start your curve or when you want to start your oscillatory behavior. When do you going to set time 0? And that is your choice. And now you will see where this initial angle have an effect on the final form of the function. But anyway, come back to our point. So you see the utility of this form now? That phi right there is your initial phase. That's it, guys.
Okay.
Because that phi right there is the leftover term when you set t equal to 0. At time 0, you're already starting your curve at phi. You got it? So if you want to start with the cosine function, if you want the cosine function, you just set phi to be 0. Okay? Or if you want like a sine function, okay, but I want sine function, you just set phi to be negative 90 or whatever. Okay, so you can adjust where do you want to start your curve by adjusting that phi. You can start from 0, you can start from 45 degree, 60 degree, 90 degree, up to you. And then the curve will start from there, and then you start oscillating right there from there on. Isn't my explanation seems to make any sense to you? Yeah, I hope. Yeah.
Okay.
All right. So that's why I just want to emphasize what I'm doing over here to be like, my point is this is really a general solution. You can use this form to explain any oscillatory behavior that has a sinusoidal behavior, And when I say sine, it's the same thing as cosine now, because you have already seen sine is just the cosine that are separated by 90 degrees apart. That's it. Okay, when you compare between these two, that's it. The red one and the blue one, they are just separated by 90 degree difference. They are exactly the same curve being shifted. Cool. All right. So I hope this maybe today is like, go way back in trigonometric functions and the calculus of trigonometric function and all this stuff. But I hope this is the connection that I really want. Now, come back to this value of x as a function of time. Once you already agree with me that this is as general as you can get, this is it. Like this will explain everything that is oscillating with the angular frequency omega. So if you want the speed or velocity, what do? Well, that's easy. You just differentiate this once. By doing the dx by dt, it will give you the velocity of this oscillation. And what about the acceleration? Just do it one more time. Cool? All right.
Okay.
So that means this is it. You already solved the differential equation that you derived from the Newton's second law, and you solve everything. You know exactly where the mass should be at any time. Checked. You know exactly how fast that mass is supposed to move at any time. Checked. You know exactly what is the acceleration of that mass at any time. Check. And you are done.
Okay.
What else do you need? This is it. You solve everything about this movement right here that we're gonna name it simple harmonic motion. Okay, the reason it's simple because it's a single harmonic. Harmonic usually means like frequency and stuff. And then because whatever you're doing over here, you have a single value of omega. Once again, omega is 2 pi f and it's 2 pi over t. So it means this oscillation have only single frequency with a very simple shape, sinusoidal shape. So that's why we call it like simple harmonic motion right here. Isn't that cool?
Okay.
All right, so that's it. And interpretation is going to be simple. We already saw it that the A over here give you the maximum possible displacements that you're going to have in this oscillation. So your A is, we call it the amplitude. That is the maximum displacement, right? Once you differentiate it, don't forget to differentiate the function inside, dip side, yeah? So what you have over here is, this is going to, by assumption over here, just to make things a little bit simple, I just set phi to 0, that's all. So over here, you get the factor of omega in the front. A is still there. So whatever numbers that come in the front for the V, that will give you the maximum value of V as well. So omega A is also the maximum speed. Nice. If you differentiate one more time, you have to dip side again. Yeah, you have to do the chain rule. You get the omega square factor out, multiply by the original A. Whatever the number comes in the front is going to be the maximum possible value of acceleration. So omega square A will give you the maximum acceleration as well. See, everything is complete. Perfect. You know everything about these oscillations. Mass attached onto a spring, have it bounce back and forth. Newton explained everything through Newton's second law, and you're done.
Okay.
Isn't that amazing here? I don't know if call it amazing or not, but it seems to me, I keep saying that starting point is so simple. It's sigma F equal to ma. But the solution, once you, make the connection with the second order differential equation, and you know the form of the solution is just simple harmonic, which is just sine and cosine, you're done. When I say you're done, I'm going to show you right now how easy it is for the future. And the future is now. Try this, guys. All right, I'm going to show you something here. And I'm going to go through the whole process one more time. Okay? And let's say we don't need to do any math anymore. We're just going to do physics here. And knowing that we have the math as our tools. Start with this. You have a simple pendulum. You have a mass attached onto a ceiling through a string over here. And at first, of course, it's going to stand in the vertical direction. And if I just displace that mass a little bit out of the vertical equilibrium point over there, let it go, it's going to swing back and forth, right? So this is a simple harmonic kind. But to show you that it is simple harmonic, this is what we're going to do from the beginning. All right, start from it. Equation of motion. Guys, give me the equation of motion. Whew. All right, enough. Okay. Look at the system over here. You have only a single mass here. Okay. Let's do some free body diagram, shall we? What are the forces acting on this mass? Well, Ajahn, mg, of course, the weight of the mass pulling it down. What else? Well, Ajahn, of course, is going to be the tension that's pulling this mass up along the string. Anything else? Nope, that's it.
Okay.
You only have two forces over here. And now when you look at this one, because you displace it in the vertical direction and let it go, it's at one particular in time, it looks like this mass is going to move in the tangential direction, right? So tangential to that an arc right there. So that means what I'm saying here is at this particular moment, you can imagine that this is the movement going to your left hand side. It's sliding to your left. So what I have over here is just, I'm just going to break the vector that is not pointing along that or perpendicular to that direction of motion, and then just do some analysis there. So what I'm doing over here is I'm going to break the mg, which is not along the direction of motion or perpendicular to it. Just going to break it into two components here. Okay, one component pointing in the same direction as the direction of motion, that's mg sine theta. The other component that I have over here is a mg cosine theta. All right, I'm just get rid of the original, fine. And because this mass is not going up or down along the direction of the string in the radial direction, there's no up or down. So that means the tension must cancel out with the mg cosine perfectly. Cool? So that's why what you have left over here is just the sliding effect over here to your left by the mg sine theta term. No problem here. Now, I just gonna apply sigma f equal to ma. That's where you get the equation of motion, sigma f equal to ma. But then you only have one f, mg sine theta.
Okay.
The only thing left for you to be worried about is the sine. Because, here, look at this. You displace the mass to your right, but the mg sine theta trying to point to your left. So what you can think of this one is like, okay, just use like a regular direction that you prefer. To your right is positive, so it means to your left is going to be negative. So that means whenever the s, the arc length that you pull to your right is positive, the mg sine theta will point in the opposite direction. And hence you have the negative sign here in the front. Okay, don't forget sigma f equal to ma is a vector equation. You cannot avoid it. So in the textbook, they say they have the subscript t just to say this is a tangential direction. Cool?
Okay.
All right, so negative mg sine theta equal to ma, and the a is just tangential acceleration. So it's just mass times second derivative of the s by dt2, I mean the second derivative. Cool. This is the equation of motion.
Okay.
Very nice. I can cancel m if I don't want to. I can rearrange stuff a little bit to make it look like what we had before. d2s by dt2 equal to negative g sine theta. But อาจารย์, I don't think I can solve this one. Right, because, well, this one is not like a linear equation. It's even worse. You have the sine theta in there, which is really bad. Okay, so how can you make things just like what we saw before? First of all, if you look at the triangle, or I mean it's a sector over here, you can see that there is a relationship between the theta and the s that we're looking at here, right there. So from the definition of the angle, theta is just going to be the arc length over the radius, right? So the arc length is s, the radius is just the length of the string itself. But Ajahn, I have it. I have the connections between the s and the theta through the length L. But what you have over here for me is sine theta. Not good. This is not good.
Okay.
How can we get rid of that sine theta? And here comes the approximation, guys. I don't know, have you noticed back in the day of high school physics and stuff, every time you mentioned about simple harmonic for the pendulum, you assume that the angle of swinging is pretty small, less than 10 degrees and stuff like that. The reason that you need this because you want to approximate the sine theta to be just the theta. Why is that? If you look further, I already captured the value of the sine theta and the theta. So this is your angle. This is sine of the angle. Can you see this? When the theta is 1 degree, whoa, these two values are almost exactly the same. Up to maybe 5 degree, you start to see 0.1 differentiations between the two. And up to about 10 degree, then the difference is about even a fraction of percent, right? It's half a percent. So it's acceptable up to about 10 degree or so. So that's why as long as your pendulum is swinging at a small angle, let's say about 10 degree, the error is acceptable. And then you can approximate this equation to look like just negative g theta. And the theta is just S over L. And so my final equation look like this, guys. Let me rewrite this. Negative g over L S. How do you like this equation? Okay, first thing first. The pendulum that you're seeing is not a real simple harmonic because we have to go through this approximation. Okay, to solve this equation, you need computer. Yeah, but anyway, if you assume that you can ignore those tiny error and all that stuff, we can still express this simple pendulum as a simple harmonic motion. The reason I say I can tell you right away it's a simple harmonic motion because, guys, look at this. From now on, as I said, we don't need to do anything anymore. You have S, get differentiated twice. You get the original back with the negative sign, with some common factor some factor in the front. You can tell right away, Ajahn, omega is root G over L. With me? And the solution of this one, I can write it for you right now. S equal to A cosine or sine, your pick, doesn't matter, omega t plus phi. And I am done.
Okay.
You see, I don't have to do anything anymore. From now on in my life, every time that I see this type of differential equation, second order, equal to negative of the original with some constant in the front, I say, hey, it's simple harmonic. I know the solution. I don't have to solve for you. I know exactly what's the character of this oscillation supposed to be. I can pinpoint the omega. I'm done right there.
Okay.
Cool? And some of you might just say, but John, why you have to work under S? Why don't you work under theta? Well, okay, I don't care. I don't mind. Because if you re-express this theta, and John, over here, S is going to be theta L, right? And I can, instead of working with the S, I can turn this S into theta L, turn this S into theta L, or, think of it, and you don't have to turn, you just keep this one. You still have that L factor. And at the end, you can write this equation in terms of theta if you want. And what do you see in the theta? Bam, bam, bam. You can see that the second derivative of theta give back the original with the negative sign with some factor in the front. I know the solution. But what is the solution? Well, Ajahn, over here, your theta as a function of time is going to be A sine or cosine omega t plus phi. It's simple harmonic anyway with the same omega, and you are done.
Okay.
Is that wow thing here? Yeah. Because the main characteristic that you really want from this one, I would say the essence of this one stay with the omega right there. The omega is the thing that you really want to get out of this one, because you just want to know what is the frequency of this oscillation. Okay, and the A, of course, you can just have to get it from the information of the system. But the point is, from now on, whenever you are hit by this type of equation, you know the solution right away. Plus, you know that the motion is going to be named simple harmonic with the known omega. That's it.
Okay.
Isn't that cool? I think it's very cool, and it's very powerful. And this is the reason why sigma f equal to ma is it's so general. It can explain anything in the universe. I would say classical universe that works, okay, and works so well. And we already had the mathematical tools to back up everything that is going to come out from sigma f equal to ma. So good. This is so good. All right, but if you don't believe me just yet, Bajan, well, all right, I heard of the mass on spring, and I heard simple pendulum, and so what? I'll show you one more, okay? What about this? You already learned this from physics 1, I think. Is the physical movement, yeah, it's a physical pendulum, so you have instead of just like a simple mass hanging with a string, then you have a real mass, extended mass, and then you displace it from equilibrium and have it move back and forth. Well, yeah, everything applies just like the same. If this mass is extended, you have like a big chunk of mass, you can turn your attention to second laws in the rotational form. Sigma torque equal to I alpha. Still remember this?
Okay.
I is your moment of inertia. Alpha is angular acceleration. The torque is the equivalent of force in translational motion. Yeah, so it's something that you use to twist the mass with the moment of inertia I. Okay, so over here, Bajan, I'll do the same thing. Equilibrium point, everything will be equilibrium, right? But then you displace your cm, the center of mass of this object, to your right and let it go. It's gonna swing back and forth. You know that. So the way that you can do is, what is the net torque acting on this around the pivot points? Bajan, there's only one force acting on this. Is the mass of itself. There's nothing else. There's no other force that's going to give you any extra torque. So the torque that you're going to get from this is mg. And if you remember back in the day, the way that you calculate torque is r cross f, of course, or it's going to be r times f, when the r is measured from the line of force to the pivot perpendicularly. So this is distance right here. This is r perp right there. Okay, so you measure the distance from the line of force to the pivot points. That will give you, you call it like a lever arms or something like that. แขนของแรง or something like that, yeah? So over here, that mg will give you that torque right there. And if you know the distance from the cm to the pivot point to be d, the r perp over there is just going to be d sine theta, when the theta is just the angle from the vertical directions or the vertical level right there. So over there, I'm done. My net torque is going to be R. Okay, let me write it here. R perp F, and it's just going to be mg times d sine theta. But wait, don't forget, this equation, no matter what, it's a second laws. So that means it must be a vector equation. So you have to incorporate the direction into it. Don't forget about that. So over here, look at this. At first, you displace the cm to your right. Remember, when you do the rotation, you have right hand rule. When you rotate your forefinger, your thumb will point to the z direction, right? That is the direction of positive directions over here. So when you displace the cm to your right, so this means you go counterclockwise, your thumb pointing toward your face. So that means your displacement over here, or the theta that you're talking about over here, is pointing to your face right there. And you call that, let's say that's a positive side. But then the torque is trying to bring this thing back. That's where the torque is trying to do. It's the mass, the weight of this mass is trying to pull this whole mass clockwise. So if you do forefinger, rotate clockwise, your thumb will point away from you into the screen. So the torque is actually acting into the page. So if you say out of the page is positive, so into the page will be negative. So that's why it's negative mgd sine theta, while the theta is positive. Does that make sense? Okay.
Okay.
So you equate that to the right hand side, I times the angular acceleration, which is just a second derivative of the theta. Whoa, so good. When I say so good, it's almost done. So let me re-express this one in the form that you're familiar with. d2 theta by dt2 equal to negative mgd over I sine theta. But not yet. It's almost, but not yet. But we know what to do next. Let's approximate that this oscillation having the theta to be very small. So you can approximate using the same approximation before. That sine theta is approximately equal to theta. And once we have that, then you can spot, it's done. See, second derivative of theta equal to itself along with the negative sign in the front. And you have some numbers in the front, some constant in the front right here. So I say it is, yeah? It's simple harmonic, guys. You are done right away. Answer is theta as a function of time is A, sine or cosine, you pick, omega t plus phi. And the omega is just going to be square root mgd over I. And you are done.
Okay.
Isn't that cool? You don't have to solve second order differential equation anymore. All you have to do is just look at the form of the equation, and then you can say it's going to be a simple harmonic with a known angular frequency. That's it, guys. I already re-expressed it one more time down here. And I hope you see the power of Newton's law right here. Okay. I don't know, you get bored with this Newton's law yet, but all right, I think this is good.
Okay.
All right, so with that, the final stop that I want to talk about this one is, once you know everything about the oscillatory behavior, the simple harmonic motion, the going back and forth, the repetitive movement and all this stuff, now you can look at some other aspects just for fun. For example, we learned so much about energy. And then, when we talk about energy, you only have two kinds of energy. It's either kinetic energy, 1/2 mv squared, or it's either going to be potential energy. But in this case, just to make things a little bit easier for you to see, let's take a look at the mass on spring. The potential energy is going to be the elastic potential energy from the spring, 1/2 kx squared. Do you see what I see here? The velocity is already here. You know everything about the velocity. The x is in there. You know everything about the position. So all you need to do is just plug in. Yeah. So look at the v. You can slide back a little bit. The expression for the v is right here. Okay, let me color code it here a little bit here. I know what the v is. I know what are the x at any time. So all I have to do is just grab this solution for the x, grab this solution for the v, plug it in there. Here. That's good. Omega a sine omega t, I pick, that's from the velocity from that page. For the x is right there, a cosine omega t plus phi. And I just, at any time, the net total energy is going to be either kinetic plus potential. I just add these two together. Nice. With the connection that we already knew that omega is square root k over m. So that means I can convert between omega and the m and the k back and forth. So that means I can write k to be omega square m if I want to. So it means, all right, every time I see omega square m, that is just k. So that means you have a common factor of 1/2 ka squared that I can pull out to the front. And whatever you have left in there is sine square plus cosine square. And from the identity, that is just 1. And that's it. The net total energy in your system stay fixed, 1/2 ka squared.
Okay.
As expected? Oh yeah, of course, right? Because it's a conservation of energy. There's nothing take away your energy, so it means your energy stay constant at all time. But the only thing that is going to get changed is just the conversion between the kinetic energy and the potential energy. Look at here. If you start right here, let's say this is your initial point, t equal to 0, this is going to be pure 100% potential energy. It's 1/2 k. And of course, if you stretch the spring to the highest maximum value of the displacement, it's going to be a, so it's 1/2 ka squared. So this is your initial energy in your system. And bam, you let it go. Of course, part of it will turn into kinetic energy. And once you reach the equilibrium point, at that point, there will be no more stretch or compression of the spring. So the potential from the spring will be nothing. So there will be 0 potential energy. And it's going to be 100% kinetic energy.
Okay.
And that's no big deal. And once you have that, you're going to overshoot this one. You cannot stop there. You're going to compress down the spring. And once you at the lowest point over here, the most compressed position of the spring, everything will turn to 100% potential again with the 0 kinetic energy. And the spring will just push everything back, and then you go back to the equilibrium point, and this one will go 100% kinetic again with the 0 potential, and the whole process just keep repeating itself. So it's a conversion back and forth between potential, kinetic, back to potential, back to kinetic, on and on. but the sum of the whole system energy stays constant. And that is why you can plot the curve right here. See, you start out from the maximum value of the potential. At that point, kinetic is 0. And in the meantime, you're just going opposite in just convert back and forth between these two forms of energy. Sounds cool? See, so all of the analysis is already built into this. Easily, once you know the solution of sigma F equal to ma, everything is pretty much solved in front of your eyes.
Okay.
Okay, right here. And that's it, guys. That's the conclusion that I can give it to you today is total energy stay fixed at all time. It's just the combination of the two between potential and kinetic energy is just change over time. All right, but the sum stay fixed at 1/2 Ka squared. And that's it, guys. We are officially done for today. Any questions? It's kind of fun. Maybe. Maybe not. All right. But I hope you learned something today, even though, well, it's a lot of mathematics, but I hope it's not as heavy as you thought initially because we were mentioning about differential equations. But from here, I hope that in your future, once you see this type of equation or differential equation, you don't have to be afraid. It's easy that simple harmonic is the solution, and we're done right there. Cool? All right, guys. So that is it for today. Oh, so are we setting up live group? Do we want live group, you think? Should we? Well, sure. That all right, guys. So I can do that. All right. So what's the best way that I can do here? Okay. All right. So give me a second here. All right. So let me stop the recording first.